All right, this train keeps moving. We are now on to 16.2, probability of events occurring together. So we already have kind of our first diagram that we worked with, Venn diagrams. Tree diagrams are another nice visual that kind of helps you organize probabilities. So this is just an example over here for flipping 3 coins. Okay. The way it works is we've already worked with tree diagrams a little bit, but you're just basically splitting each outcome and its corresponding probability. So flipping a coin, the probability of each is 1/2. Okay. And then you have that second outcome, flipping the second coin, the third outcome. So these are going to be very useful when you have compound events. And what I mean by compound events is just events that happen one after another. And what's very nice is to find kind of any of the probabilities here. All you got to do is multiply down the branches. So if we wanted to find the probability of flipping 3 heads, all we'd have to do is just follow this right down the 3 head branch, which is just going to be 1/2 times 1/2 times 1/2, which equals 1/8. Okay, and so a lot of times during these problems, when we have these kind of compound events, it's going to be very useful to make a tree diagram to kind of organize our thinking. You probably won't need to do it for flipping coins, but there'll be plenty of other examples where it's helpful. And I'm actually going to do it right here in this example here. So we have 2 yellow balls and 3 green balls placed in a jar. 1 ball is randomly chosen. Its color is noted. The ball is put back in the jar. Procedure is repeated. Find the probability that both balls are the same color. All right, so here once again we have compound events. We're picking a first ball and then we are picking a second ball. All right, notice we have this statement right here. The ball is put back in the jar. Okay, when we're putting things back, we call that we're drawing with replacement. Okay, it's gonna be a very important thing to keep track of and kind of watch out for in problems because it's going to affect our probabilities going forward. So here we're doing it with replacement, so the probabilities are not changing depending on what we pick. So it makes it a little bit easier. So I'm going to draw the tree diagram first. The first kind of split in the tree, your first pick, you could either pick a yellow ball or a green ball. To get the probabilities, it's just going to be desired outcomes over total outcomes. So for yellow balls, it's going to be 2/5. For a green, it is 3/5. The next break in the branch is going to be exactly the same. You're just now picking it your second time. So yellow, green, yellow, green. And the probability is going to be identical because we put the ball back. So 2/5, 3/5, 2/5, 3/5. All right, and so then what's very beneficial about this is, so if we're trying to figure out the probability that both balls are the same color, all right, all we have to do is kind of look at our tree diagram and figure out which branches correspond to the same color. So that would be the yellow branch and the green branch. So to figure that out, we're just going to multiply down the branches and then use our addition rule, all right, to add them together. So for the probability of 2 yellows, that is going to be 2/5 times 2/5 plus the probability of getting 2 greens, which is 3/5 times 3/5, or 4/25 plus 9/25, which equals 13/25. Okay, so right there kind of showed you the tree diagram, kind of gives you a nice visual. All we got to do is just multiply down those branches, okay, and then add the branches together that match up to what we are trying to find. Okay, so example 2, I want to do the same thing except now I'm not putting the ball back. All right, so last slide I wrote up there that was called with replacement. You're drawing with replacement. Here we're drawing without replacement. So when we take a ball out of the jar, we are not putting it back. Makes it a bit more complicated because now, as we are drawing balls, depending on what we get, it's going to change our probabilities of picking the second ball, because both our total outcomes has changed and our desired outcomes may change. So once again, I'm just going to get the tree diagram. First break is just going to be you either get yellow or green. And here, at this step, the probabilities have not changed from last time. So it's still going to be 2/5 to pick that first yellow ball. And it's still going to be 3/5 for green. Next break, you're still seeing picking either yellow or green. But here's where it gets a little bit trickier. So for this first break, the probability that you pick yellow, all right, given that you already picked yellow, okay? Well, you've already picked one ball out, so the total outcomes is now just 4. And you already picked one of the yellows, so there's only one yellow left. So the probability of picking that second yellow, given that you already picked the first yellow, is now only just 1/4. I can do similar logic for green. There's 4 total balls. 3 of them are green. So that probability is 3/4. Something to always look out for in these tree diagrams. Every break in the branch, those probabilities should be the total sample space, so those should always add up to 1. So notice we have this 2/5 plus 3/5, that's 1, and the 1/4 plus 3/4 is also 1. So let's move over to these probabilities over here. So this time on this branch, we picked a green first. So the probability of yellow, well, there's 4 total, and 2 of them are yellow, so 2/4. For green, same idea, there's 4 balls left, 2 of them are green. Once again, it adds up to 1. 2/4 is the same as 1/2, of course. All right, so once again, all right, if I want to find the probability of both balls same color, I'm looking for the probability of yellow, yellow plus the probability of green, green. So I'll just multiply down the branches once again. So yellow, yellow is the 2/5 times 1/4. And green, green is 3/5 times 1/4. So we'll have 2/20 plus 3/20, which equals 5/20, aka 1/4. Okay, so once again, just to reiterate, this was without replacement, meaning you're not putting things back that you've drawn. All right, the previous example was the same setup, just that was with replacement. Anytime we took a ball out of the jar, we put it back in before the next drawing. Okay, what we were doing there is something called conditional probability in that last example. All right, some new notation here, okay, with this bar in the middle. What this means is A given, that bar means given B. Okay, so given that the event B already happened, what is the probability of A? Okay, and so the it's going to be very important. All right, it means the event B already happened. And we're trying to figure out that event, the probability of event A. Here's the formula. Okay, we were kind of doing this without really thinking about this formula too much, but in other times, this formula is going to be quite useful to us. Remember up here, this is just that A intersection B. That just means the probability of A and B, and divided by the probability of B. Okay? Independence. Okay. So events independent really means kind of the probability that A happens is the same whether B happens or not. Okay. So like thinking about events that would be independent, flipping a heads and flipping a tails. Okay. Whether you flipped heads or tails on your first flip, okay, the probability of flipping a head the second time and the probability of flipping a tail the second time still remain the same no matter what you flip the first time. Okay, each of those events is going to be independent of each other. And we have kind of this little formula to prove independence right here. Okay, so events A and B are independent if and only if the probability of A given B equals the probability of A. So things that would not be independent are drawing those yellow and green balls in the previous example. Okay, depending on if you picked yellow or if you picked green on the first pick, the probability of getting yellow or green in the second one changes. Okay, those need to be equal. Okay, that conditional probability, the probability of A given that B already happened, needs to equal the probability of A. Okay, meaning that the guarantee that B happens did not impact the probability of A at all. Okay, so this kind of brings us to this multiplication rule. When we were actually using this in the tree diagram example, okay? Just didn't really speak about it. So this just means the probability of A and B equals the probability of A times the probability of B given A, okay? That's just using that conditional probability. In fact, this first formula is just a rearrangement of the conditional probability formula. Okay, so if you remember, the conditional probability formula, the letters are mixed around from what I had on the other slide, but it's the same idea. Okay, it's just a rearrangement of this equation. Okay, just multiplying that probability of A over that other side. That gives us the probability of A intersection B, which is the same as A and B, equals the probability of A times the probability of B given A. And when you're multiplying down the branches, that is exactly the equation that you are using. Okay, so when I did the probability of green times the probability of green on the second one, given that I picked green on the first one, that is exactly the equation I was using. Okay, if events A and B are independent, well, independence means that the probability of B given A just equals the probability of B. So you don't need to worry about that conditional probability at all. You can just multiply probability of A times the probability of B together. So that first multiplication rule, that requires that, that does not require that they're independent. The second one requires that the two events are independent. All right, so let's kind of use that rule of independence to kind of to see how we can show that two events are independent of each other. All right, so we know kind of the rule for independence. We kind of wrote it up. It's the probability that B given A equals the probability of B. Or you can flip the letters around, doesn't matter about the order. If you had the opposite order, it'd be the probability of A given B equals the probability of A. All right, so in our case, we had these two events, Jack and Spade. So let's show the probability of Jack given Spade equals the probability of Jack. All right, so let's kind of think about this. Let's do the probability of Jack first. And in order to show these are independent, we just want to show that they are equal to each other. So the probability of getting a Jack, all right, we know there's going to be, there's 52 total cards. Remember, this is all coming down to desired outcomes over total outcomes. And there's 4 Jacks. So 4 over 52. To simplify, that is 1/13. Okay. On the other side here, All right, probability of jack given spade. Okay, so that means it's a guarantee that it's a spade card, and we're trying to figure out the probability that we get a jack. So it's going to change our total outcomes. So our total outcomes now, we know it's a spade. There's 13 spades. And given it's a spade, what's the probability of the jack? Well, there's only one jack of spades. So since these two probabilities are equal to each other, that right there shows that the events draw a jack and draw a spade are independent of each other because those two probabilities are equal. Okay, so that's what you need to show every time they're asking you to kind of show independence. All right, another example here. So we have a die is rolled 3 times. Find the probability of each of these events. Okay, so it's going to be a little bit more challenging. So the first one, A, all 3 numbers are different. Okay. I'm going to try to kind of draw just an abbreviated tree diagram here just to kind of show you, because it's going to get quite crowded here. Okay. So the possibilities for rolling a die, 1, 2, 3, 4, 5, 6. Okay. And we want all 3 numbers to be different. So if we do a 1 the first time, okay, now we have 5, 6 options left. Okay. All right. Same with the 2, same with the 3. Okay. So it's going to be that 5/6 is going to be that probability for the second one. Okay. The only thing we cannot roll is whatever we did on the first time. Okay. For the third roll now, okay, now we only have 4 numbers that we can possibly roll because we can't roll what we did on the first time and we can't roll what we did on the second time. Okay. Oops, not over 36, jumping ahead here. That would just be 4/6. Okay. We can roll anything on the first time. Really, I can call it 6/6. Okay. Which is just 1. We have 5 options, because now we cannot roll what we did on the first time. Okay, so now it's 5/6. There's still 6 total outcomes. The third roll, all right, now we only have 4 options because we cannot roll what we did on the first 2, but there's still 6 total. So that is 20/36, which simplifies down to 5/9. All right. That didn't really even need these numbers here. Okay. Part B. At least 2 of the numbers are the same. All right. I wish I had a bigger neon thing here, but we have this at least flashing neon sign that we need to do some complement rule action here. Okay. So anytime at least 2 of the numbers are the same. Okay. Well, why don't we just do 1 minus none of the numbers are the same. Which we conveniently found in part A. Okay, all 3 numbers are different. That means the same as none of the numbers are the same. So to figure this out, all right, the probability is just going to be 1 minus that probability. 1 minus 5/9 equals 4/9. So there we go. This is a lot of info, but I kept it right under that 20-minute mark. Hope it was helpful.